Welcome. You write this beautiful, elegant code, but have you ever stopped to think about what happens next? How does that text actually become a running program? Well, today we're going to pull back the curtain. We're going under the hood to explore the super clever data structures that are the real brains of the operation, turning your instructions into action. Let's dive in.
So let's start with a really basic question. You've got a compiler, right? The program that reads your code. When it sees a variable you named x or a function called sum, how in the world does it remember what those things are? I mean, it can't just guess. It needs some kind of internal filing system, a way to keep track of everything you've defined.
And that filing system has a name. It's called the symbol table. Honestly, the best way to think about it is like a secret dictionary, or maybe an address book that the compiler builds just for your code. Every single time you declare a variable or a function, the compiler jots it down in this book.
So to put it a bit more formally, a symbol table is just a data structure that keeps a record of all the identifiers in your program. And that means everything, variables, functions, you name it. But it's not just the name. It stores the important details, the attributes, like is this an integer or a string, and where can I find it in memory? It's basically the compiler's ultimate source of truth. And in the real world, it looks pretty much just like this simple table. For every identifier name, like our x or sum, the compiler stores its type, int or function. This simple key-value system is the bedrock that prevents your program from, say, trying to multiply a number by a word. It's the fundamental grammar check that makes our code actually work. Okay, so a symbol table is awesome for looking stuff up, but what if looking things up isn't enough? What if we need to organize our data based on importance, on priority? What if we always need to know the biggest item or the smallest, like right this second? Well, for that, we need a more specialized tool. So let's meet the heap. At its heart, a heap is a special type of tree structure that follows one very simple, very strict rule. We call it the heap property. And that complete binary tree part, that just means the tree is filled up neatly, from left to right, with no weird gaps. The whole magic of the heap comes down to this one simple rule about the relationship between a parent and its kids. And this is where things get really, really clever. So while we might draw a heap like a tree to understand it, the computer stores it as a super efficient, simple array. And by using these little formulas, it can instantly figure out where a parent or a child is. For any item at index I, its left kid is always at 2i plus 1. No complex pointers, no wasted space, just simple, fast math. It's a brilliant optimization. Now that simple rule we talked about, the heap property, it actually comes in two different flavors. And the only thing that separates them is whether you're interested in finding the smallest value or the largest one. This gives us what we call min heaps and max heaps. So here's the bottom line. In a min heap, the rule is that the parent is always smaller than or equal to its children. This is great because it guarantees that the absolute smallest element in the whole collection is always sitting right at the top, at the root. And a max heap? It's the exact opposite. The parent is always bigger than or equal to its kids, which means the largest value is always right there at the root, ready to go. Okay, but what happens when you add a new number or change something? How does the heap keep its strict order? The answer is this amazing, self-correcting process that has a fantastic name, heapify. Heapify is a little procedure that zips through and makes sure the heap's main rule is never, ever broken. And the heapify process is just plain logical. First, you look at a parent and its kids. If the rule is broken, like a child is bigger than its parent in a max heap, you just swap them. Then you just repeat that check and swap process as you move down the tree until everything is back in its right place. All right, we know what a max heap is, and we know how it keeps itself perfectly organized. Now for the payoff. We are going to take this awesome tool and use it to build an unbelievably efficient sorting machine. Let's put this thing to work. And this sorting machine is called, you guessed it, heap sort. As the name implies, it's a sorting algorithm that is built completely on the foundation of that max heap data structure we just talked about. Its entire strategy relies on one simple fact. A max heap can always tell us instantly what the largest element is. So here's the game plan, and it's really quite beautiful. First, we take our entire messy list of numbers and we force it into a max heap. Then, since we know the biggest number's at the top, we pluck it off, swap it to the very end of the list, and basically lock it in place. Then we just heapify the rest of the numbers to find the next biggest one.
And we just repeat that process until the whole list is sorted. Okay, let's actually walk through this. Here's our starting lineup, a totally unsorted array of 5 numbers. Our mission is to sort this from smallest to largest using our new Heap sort machine. First things first, we run our Heapify process on the whole array to build that max heap. And boom, just like that, the largest value in the entire list, 10, has bubbled up to the very front. It's now the root of our tree. Now for the clever part. We take that root, the 10, and we swap it with the very last element in the array, which is 1. Now look at the result. The 10 is at the end of the array. That is its final sorted position. We're not going to touch it again. So now we pretty much just ignore that 10 we just sorted. We're now only looking at the first 4 elements. We run Heapify on that smaller group, and what happens? The next largest element, 5, rises to the top, taking its place at the root, all ready for the next swap. And we just do it again. The new root, 5, gets swapped with the last element of our smaller heap, which was 1. Now look, both 5 and 10 are in their final spots, sorted perfectly. You can see the pattern emerging, right? Heapify, swap, shrink, and repeat. After just a few more cycles of that same process, we're done. We're left with a completely sorted array. By just systematically plucking out the biggest remaining item and moving it into place, Heap Sort brings perfect order from total chaos. So we've gone from a simple code dictionary all the way to a full-blown sorting algorithm. But why does this stuff matter outside of, a computer science class? What's the real takeaway here? Well, here's what I think is most important. First, those symbol tables are the unsung heroes, the fundamental dictionaries that make modern programming possible. Second, heaps are just incredibly efficient whenever you need to handle priority, finding the most important task or the biggest value fast. But maybe the biggest lesson is what heap sort shows us about computer science itself. It's all about taking simple, clever ideas, like the heap, and using them as building blocks to solve much bigger, more complex problems. And that kind of leaves us with a final thought to chew on. We've just uncovered the hidden logic behind one sorting method. But every single time you look at a news feed, or see your search results, or browse a list of products online, there's an algorithm putting it all in a specific order for you. So the real question is, what other invisible rules are out there constantly sorting your digital world?